Alright, I think that's a good start to the stream. How's everybody doing tonight? I'm your pal Slowbeef. We're going to be digging into session 4 of ROM hacking Dead of the Brain. Just a warning. This video is, what do you call it? This video is, something. I don't know what I'm talking about. This is a dad stream is what I want to say, so my kid might interrupt. But that is life. Hydra, base camp. Come on, Hydra soundtrack. Thank you. Okay. That seems loud. Okay, so Dead of the Brain, our good friend. We got into a debug utility yesterday, but we didn't get very far with it. Actually, no, we ended up doing some coding last night, and I was not happy with the results of it. Mainly because I was trying to code off the fly. It's tough when people are, like, kind of looking over your shoulder and all that, you know? So, what are we going to do differently this time? Flying Bulbasaur. I'd like to translate the whole thing, honestly. Oren Ronin from Danganronpa. This is becoming, I should say, a bit more of a stone soup project than I realized it would. Hold on a sec. Let me just ask. More of a stone soup project than I thought it would be. You know, Drastic Action is already has a text extractor and replacer written in C#. QCR has one as well, I believe, in Python. I know he's got the extractor. Admiral H. Curtis, who did the aborted Danganronpa translation ROM hack, aborted because the official version came out. Turn down the volume a teensy bit. Okay. Weighed in with some stuff that was really helpful. Oren Ronin already translated did a first pass of the translation, a first draft of it, of the opening sequence here. And basically, Drastic discovered some new stuff. So I think my time is better spent right now before actually just sitting here writing code, because a lot of that is just going to be looking up how do you do byte comparison and all that shit. Maybe we'll write some pseudocode first, but we'll maybe from a broader perspective figure out what we want to do before we actually do it, which is probably the smarter way to do it. That popular colloquial grammatical analogy, a stone soup project. Do people not know that? Stone soup? It's like a story when the village wanted to make soup. And the person brought a stone, and everyone started bringing their own pieces of the soup, and that's how they make stone soup. No? I don't know. Any rate, enough talk. Let's jam. See how our save states are doing. Harmful jerky. What's pseudocode? Pseudocode doesn't run, per se. It's its own language, but... Alright. What did we discover last time? We discovered a lot, actually. We'll go back to our Yato thing, right? We know that for some reason BA280E are the double dots right here, and I expressed surprise that there were 3 bytes for that character encoding, especially when they have Ya, Su, To. 1 byte each for hiragana. And then even more strangely, 2 bytes for kanji. And as we also discovered, katakana. So what is going on here exactly? So before we get into what is going on here exactly, to really organize my notes a little better, we're going to stop this and this for a minute. I want to talk about another subject, arithmetic. good old-fashioned columnar arithmetic. So, in school, you've probably learned arithmetic. Columnar style. Columnar arithmetic, of course, means you go by columns. How do I want to do this? 6. Good, right? And how do you do columnar arithmetic? Well, you start with the rightmost column. Say, what's 3 plus 6? It's 9. What's 2 plus 9? It's 11. I don't have room for 11 exactly, so I'm going to carry a 1 here, right? And then 1 plus 5 plus 2 is 7, but I'm carrying a 1. So that's 8, and I'm no longer carrying a 1. Finally, 1 plus 3 is 4. Boom. Columnar arithmetic. No problem at all. We all remember that from school. So, this is great, but of course, we're working in binary here. And we talked a bit about binary last time. Numbers and things like that. We can count up in binary. We denote it with hexadecimal. Stop. You're pissing me off with that notepad, by the way. 0, that's 2, 0, 0, 1, 1, that's 3, etc. I don't have to go through the whole thing, do I? Cool, so you get the idea. So let me ask you a question. How do we do arithmetic on a bit string? Like... 1, 2, 3, 4. Yep, okay. We're going to add 2 bit strings together. 1. Okay. Well, it turns out it's pretty much the same thing, just with less digits, right? The trick with columnar arithmetic is you add 2 digits together. If you can represent it with the digit, you do so. But if it's above 9 in columnar arithmetic, the last digit, such as the case of 2 plus 9, you carry a digit over, if that makes any sense, right? And that's how you do it. It turns out it is the exact same thing in bit arithmetic. So 1 plus 0, this column, is 1. Flying Bulbasaur I will not put on the Snatcher soundtrack because I don't want Konami to get money. 1 plus 0 plus 1 is 1, of course. 1 plus 1 is 10. So we have a 0. We carry a 1. Okay. 1 plus 1 is again 10, but we're carrying a 1, so we add a 1, carry another 1. 0 plus 0 is 0, but we're still carrying a 1. Same kind of thing. Okay. 1 plus 1 is 1, I think, right? I think I got that right. Congratulations. Binary arithmetic, more or less, right? Yeah, it seems good. It's 1 byte too many for an 8-bit instruction, but it is just arithmetic, you know? So, yeah. Necrookville, do I have to know 2's complement for this? We don't right now. We might get into that, though. And I don't mind. I like explaining 2's complement, actually. It's one of my favorite subjects. It's actually what my wife and I discussed on our first date. No, okay, so... binary arithmetic. Great. Who cares? Well, I want you to suppose for a moment that we want to create something to add bits together. Okay? Like from an engineering standpoint almost, alright? And so we'll do this. We'll have like a little state here or a node or something, right? And this is what we're going to do. I'm going to draw it like this for a minute. Just hear me out here. Let's say we get an input of 0 and 0. 2 bits, 0 and 0. Oh, and we can only output 1 bit. Remember, we're doing a column at a time. So if I have 0 and 0 in my column, I'll output a 0. Okay? If I have... and you're wondering probably why I'm drawing these little loops. You'll see in a minute. If we have a 0 and a 1 input, we'll output a 1. I'm just doing these slash to demarcate it. I'm drawing with a trackpad too, sorry about that. And of course, if we have a 1 and a 0, same thing, we output a 1. With you so far, says Ferreter says. But here's the issue. If we get 1 plus 1 in our input, and we can only output 1 bit, what the hell? What are we going to do? Well, if you look at the column, 1 and 1 makes a 0. But we're now carrying a 1 over. And if you look, when we carry the 1, things kind of change. So instead of looping back to the same node or state, let's create a second state. Tell me if I'm going too fast or doing weird shit here for those of us not in the know. I see you all writing DFAs. So we'll call that N, I guess, for normal state, and C for a carry state. Carry state means that we're carrying a number. So this time around, we get a 0, 0. Remember, 0 plus 0 is 0, but we're carrying a 1. So if you notice, it's the opposite output. Oh, but what's that? We're no longer carrying anymore, so we can go back to our normal state. So we get, if we have 1 and 0 together, remember we're carrying a 1. Shanty, what's going on here? I just came in. We're talking about how to add binary together using columnar arithmetic, just like in grammar school. Anyway, we have a 1 and a 0. Would normally make 1, but again, we're carrying a 1 here, so we output... Oh, sorry. We output a 0. And we're still in the carry state. I drew this pretty silly. 0, 1, of course. We're in a carry state. Have a 0. We're still carrying. And... yeah, actually, I can't erase with this sketch it, unfortunately. And, oh, I have 151 people watching this crap. Awesome. You all have no taste, but thank you. If we add a 1 and a 1 together, we output a 1, and we continue in our carry state. So, this is a weird diagram, but the idea is, what we're doing, this is more or less a flowchart for how to add columns in binary, how to do columnar arithmetic with binary. Let me show you one more time. Let me make an easier one. We'll do 1000 plus 1101, okay? So we're going to add these together. So column 1, 0 plus 1. We'll go to our little system here. We say I have a 0 and a 1 as an input. I will output a 1 and remain in normal state. Okay? JuiceDuke20, do you really need to deal with binary ever? Yeah! Just a reminder, everyone. When you're doing ROM hacking and shit, for real, all this hex and shit is notation for binary. I'm not, like, doing this just to show off. Like, I'm going somewhere with this. Don't you worry. You do need binary for ROM hacking. Sorry. Anyway. What do you call it? He sounded so scandalized at that question. I was scandalized. Thank you. Anyway, look. We're going to the second column, right? Not get too distracted here. 0 and 0. We have a lot to do tonight. We output a 0. It's this state right there. Boom. Alright. 0 and 1, we know it's a 1, just like before. 1 and 1, we output a 0, but we're in a carry state now. Okay? So let's add a couple more things. Just add one more bit to that. Okay. Remember, 1 and 1 make a 0, but now we're in a carry state. So what is 1 and 0 in a carry state? It outputs a 0, and it stays in the carry state. Because we're still carrying a 1. This is basically a diagram for how to do columnar binary arithmetic, just not in your head. You can just follow these sorts of instructions here, and you'll get it. Now, here's the question for you. Oh, I'm sorry. What we have done here is we have created something that certain people in the computer science community call, and because they called this at my school, an FSM, or a finite state machine, otherwise known as an NDFSA, or a non-deterministic finite state automata, excuse me. Or I noticed some of you are calling it DFA, which I'm guessing is deterministic finite automata. I don't know. The point is that we have states, right? We have inputs and outputs we present. But when we're doing this binary addition and shit like that, we need to hold on to states. We need to, like, change states and say, okay, the inputs and outputs are actually going to change depending on what state I'm in. This is a thing called a carry adder, this particular machine that we've talked about here. You can link a bunch together, so you can do, like, a bunch of these at once. You'd call it a carry ripple adder, etc. So so what's the point of all this? Why did we learn about finite state machines? Because they're everywhere. I want to go back to Dead of the Brain now, if you don't mind. This is what we know. We're not going that low level yet, by the way. I want you to suppose the system is in a normal state, okay? And it encounters a 70. We know that it's going to print hiragana. So I'll denote that like so. So maybe 70 output to hiragana, right? I wrote that like a 2. Same for 4F and 5-4, so maybe there's a range we can accept just so we don't have to draw all of these things, you know? 4F to 70 will output here. Well, that looks so ugly, I'm sorry. We'll output hiragana. And it'll just go to the next byte and keep printing. However, if we get something like an 83, or in fact, if we get anything from 83 to, I think, 9F, I can look that up, but the point is, that character range, if we get a byte there, we are in Shift-JIS mode. And what that means is, when you get an 89, here, for example, I know that I want to write a kanji from a certain range, and the C6 tells me exactly which one. In other words, here I was taking one byte at a time and returning back to normal state. Now, I'm, 89, the 89 tells me I'm going to be in the kanji state, the C6 tells me which kanji I'm going to draw. In which case, it is this one here. And then once I've drawn that byte, whichever it is, which I guess it can accept anything. So F, whatever. I'm going to return back to normal state. And now that I'm back in normal state, I encounter a 57. I know from my state machine that is in the hiragana range, so I draw another hiragana. Tsu-i-ta-ka. And I do that, and I draw more and more bytes. And there you go. So, what's made things weird, though, is we've encountered these very odd BA type of things. And BA280E appeared to be punctuation, which is strange. BA23, right here, seems to denote the coal name tag, koru. And sure enough, just to prove that out, by the way, if I change that to a 24 in code, and in memory, and reload the save state, it's going to change from coal to kuga. If you notice now, it now has 4 characters in it with the colon. And if I change that to a 25, load again, just like last night, it's going to change from kuga to jock. Or something else. 22 maybe I meant. Did I mean 22? I don't know what that is, actually. Who We just try 22 real quick, see what happens. I don't think this will work. So the point is, something weird is happening when we do BA. That BA byte seems to mean something else. Yeah, it broke things. Weird, right? What's going on here? The answer is that the character BA is called a control code. And what it does is, when the text reader encounters it, it brings us to some kind of control state. Okay? And in the control state, if we get a 23, a 23 will output sorry, the col tag and bring us back to normal state. A 24 will output the cougar tag and bring us back to normal state. See what I mean? So this is how the finite state machine works as we go through reading character by character. Any single bytes from 4F to about 70. I'm sure the range is bigger, by the way, but we'll kick out hiragana. Anything 83 to 9F will pick out katakana or kanji, just like Shift-JIS, and return us back to normal state when it reads the second byte. And the control codes, what we're interested in, will tell us different things. So here's the deal. All right, right now we know our range. We think our range of katakana is 4F to 70, which I don't agree with. I don't think it's that. In fact, I know it's not. Hiragana, uh-oh. Sorry, I got the baby here. Let me just see what happens out of that. Oh, D4, W. Oh wait, no, I'm wrong. Hold on. 4F is small su. He's katakana anyway. What am I doing? You might wonder what I'm doing right now. Just give me 1 sec. Hiragana is usually 82, but not in the case of Dead of the Brain. Alright, fuck Sue. There it is. 63. 22 in hex. It's 22 in hex. So, one sec. Normal state. So, minus 22. So I think 2D 70. 70 is what? Ya? I'm just kind of referencing, like, I know 42 is the small su in Dead of the Brain. And the first character in Hiragana is the small a. So I'm going up. I'm subtracting 20 hex minus 2. 22 hex. So, since I know that was 4F minus 22 hex makes it 2D. 70 was the highest range I knew. I'm going to posit that. Just reload my save state. Alright, Ya. Ya is 70. Let's go back to our code page here. Find Ya. Ya. Ya, there it is. And it looks like hex plus 10 minus 1 is a 70 plus 10 minus 1, 87F. Alright, so my posit is 2D to 7F. Print hiragana character from to you. Okay? That's what I think normal state does. 83 to 9F? Let's see. Yep, 9F, cool. 83 to 9F. Go to katakana. kanji mode. So this is what happens after you read a byte, by the way. Katakana/kanji mode. So after that, if I get a character... Well, this one I think, no matter what I get, I'm not sure, though. And while we're doing this, let's prove this out a little bit. Because I say my bounds for the normal state are 2D to 7F. So... take our good old yato, the first sentence of the game. We'll start with... I should get lowercase a, and then uppercase yo. Not lowercase, but small and big yo. Alright. Sorry I jump around, but I'm kind of scatterbrained. Yeah. That's a yeah. I didn't expect that. Oh, mistyped. 7F. Yep, and N. That's it. Capital N, right? So that's the limits of our hiragana. In katakana kanji mode, I think... I'll put a question mark here. We don't know yet. But I think any character... Print... Go to normal mode. So we're writing out our finite state machine at this point. And we also know that BA takes us to control mode. Okay? We know that if we get a 23, print Cole name tag. At 24, we print Cougar name tag. I could swear 25 is a third name tag. That is what Drastic Actions found in subsequent MES files. He's gone a little ahead. Whatever. But the point is that control mode. We have a BA23. But I'm still curious what the fuck was going on with this. This BA28OE that happened twice and seemed to represent these two sets of double dots. And then Admiral Curtis noticed something. And I don't know if he's right. I haven't tested it, I haven't looked at it. But I want you all, if you could, to take a very close look at those two sets of double dots on screen. Ready? New game. Let's watch very closely at those sets of double dots. Watch the text. Specifically, how the text animates on screen. Did you see that? Okay. The Cole tag appeared instantly. The two ellipses appeared instantly. But then every other piece of character blitted in, like beep, 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 like in Phoenix Wright, you know, or something. Let's reset that again. In fact, let's take a save state so we can go a little closer to it. Yeah, it's right there. So, that's weird. Sorry, let's just do that again. I think I wrote over this. I think I had a little race condition with the save state there. Drastic Action says, if you see BA28, the next character will be a symbol. I'm gonna bet you're wrong. Even though you've been looking at this much longer than I have. And, yeah, K-Vector is absolutely right. It looks like BA280F is the period at the end of the sentence. Oh, maybe he is right. Damn, I thought I had something there. So, let's ask this. I guess what I'm saying is, what if we put BA 28 in front of the 54 here? The ya. Then after the conjugate, we have a BA 2830, a BA 28. Or no, we can't do that. Okay. All right, let's see what happens. Awesome. Oh no, that's what I was thinking, that BA28 was something like, hey, immediately draw. That's awesome. Alright, drastic actions, you got me. You did it. You were correct, I guess. It looks like BA28, in fact, is punctuation of some sort. Alright, so I guess with when we get a 28 after that, we go to punctuation mode, I suppose. Punctuation mode. We know that 0E is double ellipses. Go to normal mode. Damn right, you're right. Yeah, I will totally concede that. You had it. Period. Go to normal mode. That's so weird. So BA28 puts you in the sort of punctuation thing. And by the way, hold on a sec. I just want to confirm. BA25 is the third name tag. Yeah, that's the thing, Batashu. Like, he's saying 3 bytes for a punctuation character, and that's when I'm like, when Curtis mentioned the thing, like, that the ellipses came in, I'm like, I bet you 0E is actually the punctuation, and the BA28 fucks with the speed of it. 25 is. Okay, yep. Go Get Mailers says, what have we all learned? What have we learned? Says, says go get 10 nailers. Well, we're learning really the state machine that the text reader writer is using and stuff. And the idea is that when we go to write code, we're probably gonna want something that's a little mindful of all these modes somehow. It's a little tricky with kanji mode because it's easier to just print out the second byte for shift.js, but whatever. It's easier to kind of organize the code and stuff that we're gonna write, or that someone's gonna write, or whatever. I do intend to write this. I don't know if I intend to write it on stream or not. Now, this is all nice. We can keep guessing and stuff, and I am curious what BA 26 and 27 could do, actually. Let's fix this. This is my favorite song in Hydra, by the way. No, it's not. The one after it is, but I love this one, too. This is Path of Scylla. God, I missed that game. Oh, I turned off the text speed, right? BA26 is after the period, says K-Vector. Ah. So we know what BA26 is, I bet. Whoops. Hey. Save. Are my save states not taking? What's going on here? Sorry, hold on one sec. Stay here. Sorry, just give me one sec. This is the one I like. There we go, yeah. Sorry about that. Okay. Yeah, look at that. BA26 starts here. I think, so this ends the dialog box, right? BA28F is this, and this signals end dialog box stop printing. It's like our terminator. So 26 is terminate. Honestly, I think all of these go to normal mode. Now, obviously, you don't have to diagram a whole finite state machine, but you could make a flowchart out of it if you like, or some UML or something. I think that's overcomplicating it. But the point is, we would like to have some idea what this all is doing, because later on we might encounter other new control codes and things like that. 26 ends it. What does 27 do? Do we have one? Let's find out. Oops, BA27. We have some, but it doesn't look like... Eyeballing it. This really doesn't look like text around it, so I feel like we're somewhere else in the file. Am I wrong on that? Yeah, we were far away. I am very curious what BA27 does, so... let's say we find out. Kitty? Black Fang. In theory, yes. In practice, a couple people did it. But yeah, we'll be doing that. Neither do I. I don't know what Kiru is. So we'll just add some question marks. This is the music from Hydra, by the way. Black 8 Descent. A short soundtrack. But... alright. Where were we? This guesswork's fine. It really is. As far as when I parse... yeah, so we don't know what 27 is. Alright, so... this is all fine and well and good. I still want to know what the fuck this is all doing. What do you say we make a breakpoint and try and catch the assembly when it's using these bytes? Sound good, Yang? Alright, what am I talking about? There are things called breakpoints. And when you run a program that can be debugged, such as a debugging emulator like Neko Project 21 Debug Edition, what you can do is you can set two types of breakpoints called execution breakpoints or memory breakpoints. When a breakpoint is hit, it tells the running program, stop execution and show me some shit. Show me the state of memory, show me the registers, show me the instruction you're running. Things like that. Execution breakpoints say, when you execute this specific instruction, stop. Memory breakpoints, which is what we're going to be using, are going to say, when we read or write to a specific byte in memory, stop. And show me what you're doing. Let's see here. Now, Oren says Kiru is a character later in the game. That's interesting. So, alright. So what are we going to do? Now, I'm going to tell you the issue here. In a 32-bit system like a Sony PlayStation, something like this, 40A00, That's the memory address of this first character, the 54. And if you look along the columns here at the top, 4DA09 is this BA right here. And what you could do is you could just set a memory breakpoint to that exact value in memory, mind you. Remember, we have a save state header we have to subtract. And say, stop execution when you read that. Unfortunately, we have a 16-bit PC98 here. And 16-bit means the highest value in memory we should be able to address is FFFF. If you notice, we are looking at, right now, 4DA00. Here's the bad news. This is way higher than FFFF for the seemingly addressable space. So what computer architectures do in this state is, that's right, Harmful Jerky, 65535 in decimal. What they do is they use this thing called segments, where they cut the memory into like pages or segments. So you have something that says, I want to go to this page in memory, and then this offset from that page. Alright. This is memory. It's using all absolute values. Looks exactly like our save state, minus some headers. And if you notice this little thing in the bottom, oh, that's convenient. This little thing at the bottom here says real mode. That's why it looks like our save state. But let's make a breakpoint, shall we? Ronan told me how to do this yesterday. It's like under... Ah, shit. Where'd you say the breakpoint? Where the fuck are the breakpoints? Select the location and press F2. Oh, alright, we don't even have to fuck with that stuff. Awesome. Then awesome. We don't even have to worry about all that memory paging shit. Fuck learning things, and I'm happy with that. I'm totally serious about that, by the way. I don't want to learn this. Alright, here's the deal. We start at BA, which, as I said, was 4DA00H. This is the first byte read by the game. Part of BA... I'm sorry, I'm wrong. Not by the game, excuse me. It's 4, right? Yeah, this is the control. BA is the first control code for this col name tag. It's the first piece of dialogue we're reading. It is at 4DA04. Bring out our calculator. So, 4DA04 minus a 230 hex editor. So in real memory, this should be at 4D7D4. So let's go back to memory. Look at that. And I think BCA2, yeah, see this BCA20E? BCA20E, and if I remember, yeah, that's the beginning of the Open1MES file. So this is where it is in memory. 4D, 7D, right here. Press F2. Yeah, alright, I guess that worked. Hold on to your butts, motherfuckers. Alright. Alright, paused because it just read that. It would be really nice to show me the instruction it's running now. The fuck? Alright, so extended EAX. Oh, should I explain what this shit is? Alright, node menu, thank you. Not the stack. There we are. Oof. Well, this is going to be interesting. Alright, so I'm relatively new to x86 assembly, just to warn you. But, where's new window? Here. Alright. Stopped at BA, down here. On this CMP, which is going to compare the lower portion of the A register, which is 0181, right? Or no, is that just 81? So the first thing this is doing, I think it's comparing it to 81 with SI. Can use zoom, says Harmful Jerky. I don't know, truthfully. Hold on. Can I copy this? This is where things are gonna get hairy. So. Alright, so I did read up on this on x86. The CMP operator is going to compare two operands and set a Boolean. It's going to set. There's like a thing that like stores all its flags. Well, the point is it's going to set a Boolean. And then this is going to say jump and is that jump not zero? Non-zero. Basically, CMP really subtracts the two operands and throws away the it uses that to compare two operands. So I think this is going to jump to DDF7. What the f... That's throwing me. What the fuck is SI? Let's look here. Oh, ESI. Here we are. 90D4. What the fuck is 90D4? 90D4. Oh, I know what 90D4 is. That's memory. It's okay, the bracket. It's comparing memory. Haha! Okay. Here we go. I know what this is doing. This is comparing SI, right? This is in that ESI register, which is 90D4. Shit, okay, so. ESI, well, SI equals 90. What was it? 90D4 is what I said? Yeah. That number seem familiar? I bet you that number does seem familiar. Because this BA was at... What was it again? Wrong one. It's at 4DA044. Which is really... Alright. In real memory, that was 4D7D4. Where the fuck's my notes? I'm losing track of my windows. No, there's no pad. Okay. So, 4D7D4, right? In real memory location is what we're reading. Notice the D4 here, right? Okay. Haha. Oh, I know what this is. We're using segments, remember? So here's the trick. 4D7D4 minus the stack immediate. I don't know what that SI is. It stands for. I only, whatever. 44700, right? Alright. So what did that say? Alright, so it's... So the question is, what's 44700? I'll tell you what that is, motherfucker. I don't care about you running game right now. Okay. See this 4470 right here? Or wait, ES 4470. Is that the extended segment? Okay. So the 4470 is basically when we're looking at segments. Yeah, I think it's adding. It's using 4470 to set the segment in memory. Segmenting is where this gets really hard to follow. Yeah, I'm actually kind of not getting it. Thank you, Ferreter. Yes. The end goal is to translate the game to English. Right now, that means reverse engineering how dialogue is stored. All right. So it's going to compare the value at that memory location, which we could kind of have guessed, honestly. I'm losing track of my windows here. No, where's the fucking assembly window here? All right. And then it's going to do a JNZ to DDF7. Oh, check that out. There's 4470 on the left. Okay. So it's going to jump to DDF7 down here. If it is, I believe, AL, which is the lower order byte of the AX register, which is 81 right here. So I think this is comparing 81 to what's ever in memory, which is BA. So this is going to fail. The comparison is going to fail. J and Z. Jump if not 0. Yep. Flag of CF equals 0. Okay. Yeah, jump if not 0. So, okay. How do I... I want to step over, yeah. Why can't I do that? I didn't start running the game again, did I? No. Wait, I think I stepped over. Okay, it's going to jump not 0. So I think the comparison operator should set the ZF flag to not 0. So I think it is going to jump to DDF7. So it looks like... Alright, so that means 81 was special. right? Because it compared it to EAX, which was 181. Still hide our original soundtrack, by the way. Bonus trailer. I like this soundtrack a lot, so let's just continue with it. Alright, I think this is going to jump to D. So 81's important, is my point. String and array copying is doing a jump not zero and comparing to what's in that register and then so 81 is a thing. 81 is a special thing. We know that because it's going to jump somewhere depending on 81. So let's hit step over, I think, right? Or is that step into? Oh, step into it. All right, DDF7, show me what you got. Why did we go here? Why did we go here? Why did Hide Array stop playing? Oh, dumbass. Why did that... Why the fuck did that jump here? Shouldn't it have jumped to DDF7? Wow, this is totally weird. Sorry I can't zoom. Actually... Hold on. Done under ease of access center.
Always scan this section.
Huh? Stop that. Thanks.
Soldiers, future of humanity lies in your hands.
Is that better? Kind of.
Unit 87.
Why is it appearing there? Alright. This is what I was talking about when it was comparing... well, here, let me show you. Side by side here. Alright. Just gonna push DS onto the stack. Zor AXAX. Why is it doing that? Holy shit. This is not quite what I expected. Zor AXAX exclusive OR. Well, it's always 0. Wait, or is it Zor AX? Yeah, okay. And you can see it made AX0 from 181. Right? Okay. It's going to move AX into DS. DS is the data segment. So it's going to go 0, 0. So it's going to what? Reset the data segment? shit, sorry, I didn't realize I was zooming in on that. In AL43. What is in? Oh, here we go. Yeah, let's do that instead. That's smarter, I think. Magnifier. How do I turn off the fucking magnifier now? Oh. Fuck you. Yeah, OBS is a much better solution, thank you. Let's see. Sorry, one sec. Ah, shit. Wait, sorry, one sec. Monitor. Subregion, subregion. Is this better? It's black. You'll see it in a sec. All right, better. Tell you what, let's reload state so we can all look at that together. Okay, so it stopped because it's about to read. It read, excuse me, or it's about to read. Sorry. It's about to read, as you can see up here, CMP bracket SIAL. Okay, what is that? We have 4 maiden registers to work with here. EAX, or they're usually called AX, BX, CX, and DX, okay? AL is the lower order byte of AX, which is currently set to 81. It's comparing that with SI, which, as you can see here, SI is 90D4, and when it's offset by, I think the data segment or the code segment are the same thing. That's weird. Whatever. Actually, they're almost all in that data segment, that memory segment. The point is that, where's my calculator? 44700 plus, what was it? SI D90D4 is 4D7D4, which is the BA right here. So yeah. So it's comparing the BA at that memory location to 81. So let's step over, right? I think we want to step over. No, let's step in, I guess. Alright, so we step in. This, I believe this fails because, yeah, it should be N0, NZ, which is true. We're gonna jump not 0. Hey, what's up, Ricksoft? We are Translate ROM hacking a zombie adventure game for the PC-98. Jump not 0. is really the fucking... No, this is not right. Hold on. 2 values are equal. The Z flag is set to 1. It's not, so it's 0. The jump will take place if it's not 0. So this jump will take place. Look at this screenshot. I am interested in what he did. Very nice. Thanks, Drastic Actions. He's way ahead of us. Alright. It's going to make the jump because it's not equal to 81. So 81's a big deal. For some reason. Yeah, police knots, but this is going to be a lot easier than police knots, I think. I play games like, of course no one's already released the ROM. You know, definitely not on PC 98. Drastic, you are very good at this stuff. Alright, the thing that's going to confuse me is this is going to make a jump. And this will get faster as we learn more about it, right? So this is going to jump not 0. It's just a 46 is the opcode? This is going to be such a fuck... I hope we don't have to write some of this. Jump not 0 to DDF7. If I'm doing a jump, I think it's going to be to a code segment. Gulp. Code segment, so... sorry, going back to my other window here. God damn it. No, the other one. Alright, DDF7. I think it's going to be code segment. Doesn't matter, all the same segments, I think. Or wait. Load IP with the value. Relative jump with the 16-bit pointer. Oh, all right, got it. Sort of. Okay. It's gonna jump. It's gonna jump DDF7 ahead. Where is it right now? I just want to prove something out. This is at 4470, right? This instruction is at DDD7 524D7. Okay. Hold on, this could be good. Plus a 230 header. 52707. $38.04 right here. That. Did I write down a 3804? I did. Yeah. The 38.4, right? 3804 right here that I'm highlighting, that is the binary opcode equivalent to the assembly instruction CMP SIAL. I should probably explain how. Except I don't understand it myself. No, I don't know enough about the opcode mapping. More or less what's happening here. Wait, what happened? More or less what's happening here is... Okay. I just wrote binary 3804. I don't know how this is broken up. Something in here is saying, like, this is a J-type instruction, maybe. these bits like all stand for different things in the opcode. There are like arguments in here, like this 0 might mean jump to AL. There's like a one-to-one mapping between these functions and these arguments is more or less what I'm getting at. If I had an opcode instruction set for the PC98, I could show you exactly what I mean, but I don't. We'll maybe get into that next time. Enough of this, though. This will go faster once I kind of understand what the fuck any of this is doing. Alright, so what did I say? I was at DDD7, right? If I jump not 0, I should jump ahead by DDF7 to take me to 604 FE. So I'm gonna jump. Which apparently 604 FE. Wow. Okay, I have no fucking idea what that does. We'll just jump. Wow. Alright, I did not expect any of this. Wow, x86 is a fucking nightmare. Size 2 and E0. Are these relative jumps or absolute jumps? Woo! Fuck if I know. Alright, we're going to push registers onto the stack, which means we're going to be using a lot of variables. Holy shit! Look at that. Alright. We push AX, so watch the EAX variable in the other window. Register, not variable. Nothing happens to it, but we push the stack. Same with BX. Notice the stack pointer, ESP, is incrementing. I can explain what that is if you like. Decrementing. Decrementing? The fuck would it be decrementing? Wow, I do not understand this fucking architecture. Alright, we're going to move the code segment, CS, into AX. For reasons I'm not sure. We're going to move the data segment, DS 4470, which is what we were reading, into AX. No, we're going to move AX into the data segment. Wow, what? And then we're going to move AX into the extended segment. Alright, so we're setting all three memory segments to 15555. I should explain the stack, I guess. The stack might grow downwards. Yeah, I guess the stack is growing downwards. Let me pause a second. Should I? Stuff here. Please explain. You got it. Alright. Alright. I'll explain. How the fuck do I explain this? Easy, actually. This is very simple. We're gonna write some code right now in a little language I invented called, I don't know. Bucket. Bucket, yeah, that's the language. We're gonna have, int x equals 5 and fuck it. And we're gonna have a function. No, we'll just have an if block, why not? If true, x equals 3, print x, what the hell? Print x. This is human readable source code any jerk could write. It's wonderful, it's beautiful, it's in a language I totally made up. I don't even think it is compile, but here's the question. What happens when I do compile this into binary? The answer is it becomes this. This is what is happening to your code when a compiler is done with it. Source code that we write in C and all that shit, gets put into all this crap. So, in normal languages, we have variables. And we have variables up the wazoo. Fuck it. Make some more variables. I don't even care. Variables, variables, variables. I love variables. Awesome. Look at that. 5 variables. The question is, what is really happening behind the scenes? There are little bits of onboard storage in the computer called registers. They are super temporary, and you get very few of them. In the in the x86 architecture, it appears you get 4, known as AX. Well, you get more than 4, but the ones for like variable purposes, where you want to just like store some data to do shit with, you have 4 variables to work with: AX, BX, CX, and DX. That's it. Kind of. Any assembly programming we want to do, we are going to have to work with 4 variables max. But, as you can imagine, for some operations, we're going to need more than 4. That just can't work. It just can't. Okay? So, let's go back to this. Let me ask you this. What's this going to print out? Well, when I run this program, I set x equal to 5. I print, and it prints 5. I enter a new block. It prints a 3. Would anyone like to tell me what the third one will print? Will it print 5 or 3? Go ahead, tell me. Because I don't really know. BlackFang666 says no. It won't print. I think it'll print 5. Ah, Rustic Earthican. Depends on the language. Actually, you're right. Aha! Yep, Sith20 has it. If you have a... Very good. If you have a local scope inside the block 5. Exactly. I do have local scope inside the block. Scope is kind of a thing that happens in computer programming languages where you declare a variable, and that variable is life. This x, basically, is not actually the same as this x. What's happening is this compiler is associating these variable names into a thing called a symbol table, which is... Well, it's going to figure out if it goes in a register or what. But the idea is that when you go to local scope and you go down a level, we push this block into a stack. Do I need to explain stacks? Yeah, the scope in my language sucks. Don't worry about it. You need to redeclare X in that scope for that to be true. You're right. I'm sorry, I do. Always explain stacks. Please do. You had to explain hexadecimal, just explain everything. Fuck it. All right. This is getting way off course. I didn't plan to explain any of this stuff. Sorry, the scope thing was kind of half finished in my head. All right. What's a stack? Alright, a stack is a data structure. It's, what is it, LIFO? Yeah. Last in, first out. So if you want to store a bunch of shit, alright, so let's say I give you A, B, C. Yeah, you know what? That is a better example. Thank you, Hail Cyanic. It's a pile of shit, like a stack of books or something, right? The first thing you put down, and then you put like another thing down on top of it, you sort of pile it up, and then you can like actually take stuff off the top of the stack, like a stack of plates. Yeah, I didn't expect to explain this tonight. So if I have like A, B, C, D, E coming in like that, I'll push A onto my stack because it's the first thing. Then I'll push B onto my stack because it's the second thing. I'll push C on my stack, it's the second thing, D and E. Right? That's a stack. And the idea is if I go to pop something off my stack, I'll take the last thing I put in first. The last in is the first out. I'll pop a D off my stack. Maybe if I get an F later, I'll push that on top, etc. The point I'm getting at here with stacks is like you have this list that's growing out and out and out, like A and B. You can see where my cursor is on the screen, F. When I pop stuff out, I'm like grabbing from the end of the list and working my way back toward the beginning of the list as I pop, and then I grow my list out again as I get more shit in there. Alright, so yeah, you basically push and pop the stack. Alright. I have 4 variables, like I said before, right? So, like, int x equals 5, and I'm going to call a function, I'm going to declare a function down here called foo. Int x equals 6. And I'll call foo here. Alright, so maybe my compiler says, hey look, this dude's only got 1 variable. I'll just set ax equal to 0. Well, this is EAX extended AX, but 0, 5. Done. Then maybe I have y 6. 7. Alright, I don't have to write all this out, but alright, I'll use the second register, EVX, for this. I don't know why I'm dividing it. I should be double quotes or whatever. And then DX is this. Okay. I am officially out of variables. Well, shit. What do I do when I call this function when I'm compiling it? So, the idea is I want to write this register somewhere in memory. I want to hold on to them because when I exit scope, when I come out of this function, I need to remember what all these previous variables were. Okay? I'm out of registers, though. I can't hold on to them anywhere, so where do I put it? I put it somewhere in memory is the answer. So in memory, I'll write a 5, a 7, a 6, and a 4. I'll run my function foo, and when I'm done with the function foo, I'll just read these 4 values back into my 4 registers, and everything will become the same. What I'm basically doing by writing this shit into memory is I'm pushing it onto a stack, okay? To help explain that, let's say there is a second function called bar. Bar had int x equals 9, y equals 11, right? Okay. So here's what I did. I wrote these values into memory. They're somewhere in memory. I don't have to worry about them. I'm in the function foo. I need to store x since the first value, that 5 from AX, is in memory somewhere. I can overwrite it with a 6. Not have to worry about it. Shit, though. I'm going to call bar, and maybe I'm going to run into that same problem. So you know what I better do? I better store the value of that into memory, too. That way, when, I'm still, like, kind of trying to do it a little high level here. That way, when, I call bar, now I have, like, I can write over all of my registers again. So I can set EAX to 9. These are my variables, keep in mind. EBX to 11. This is hex, I forgot to tell you, yeah. And then, were I to call another function, I could just quickly write these things to memory. That's all great, but, you know, this is nice in theory to say I'll just use memory for storage, for storing old variables until I need them again, right? Because then when I'm done with bar, I can pop the 9 and 11 stack, put them back into A and B. I'm done with foo. I can take the 6, pop it back into EAX, and I'm done with the... I go back to my main context, and I can pop the 5, 7, 6, 4 variables from memory. I'm kind of winging. Is this making any sense? I'm kind of winging this. No. Please. I'm getting it. Alright. Let me keep going with this. Since I'm out of variables, I theoretically just write shit to memory in like a stack kind of system, and I pop it. Here's the thing. Fuck theory for a minute. How do you actually do this? The answer is that when you call a function in assembly, we have a special register called the stack pointer, okay? The stack pointer is going to point here, and this is a memory location. Something like, pointers are just numbers, so it's something like 526E0, you know? And sure enough, if we look back at our memory, our, like, registers and shit, excuse me. See this thing? This is extended stack pointer, FCA. Okay. Cool. Alright, so... Alright. I see, it's not stack frames. They just do it like that. Yeah. Alright, hold on. The general idea is still the same. Don't worry. Don't worry about why I'm doing this right now. Alright. So stack pointer is a real memory location. When I push something onto the stack, I write it to memory. And the stack pointer, thanks to the architecture, will increment to the next spot over. And I can just push, 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 and the stack pointer will keep incrementing. Or it'll move over, basically, to the next spot. So just to review what happens in this weird case. Okay. I have 5 registers. AX, BX, CX, and DX. When I declare int x equals 5, I'm going to store it in the first register. I'm going to declare int y equals 7. I'll put that in my second register. D equals 6. A equals 4. I'm out of registers now to play with. I'm going to call a function called foo. What I'm going to do is I'm going to push AX. And in memory, the stack pointer, it's just pointing to some blank memory that I can write to. So 5 gets written there into the stack. I'll push BX. I don't have to type this out, do I? I'll push BX, CX, and DX. Now these values are written into memory somewhere. I don't have to worry about them. I can now overwrite my A, B, C, and D registers safely. So when I call foo, I set AX now to 6, and I'm fine. Oh, but what's this? I'm going to call another function, so just to be safe, I'll push A6 again. Okay? Then I call foo, or bar rather. I'm setting X to 9 and Y to 11. So 9, 11. Never forget. Sorry, I just picked those numbers randomly. So what happens now is, I mean, hopefully I did this for a reason, and I did something useful with these numbers. Now that I'm done with 9 and 11, when the bar function ends, I'm going to call something like pop AX. Pop AX is going to decrement or move the stack pointer in the opposite direction, take the value off of the stack, and put it in a register of my choosing. Stack pointer moves back. And then, as I exit other functions, I'm going to pop it again. I didn't need to here, but we'll do it anyway. We'll pop CX to get the 6. We'll pop BX to get the 7 back. Pop, pop. And finally we pop the 5. And our stack pointer is in the original location, and our 4 variables have the original values now that these functions have ended. That is how you more or less do things when you need more than 4 variables. You temporarily write it to memory, and you're given the stack system by the architecture to help you do this. What was I saying next? Remember, by the way, again, the stack pointer is just somewhere is just a memory location. It's just a number. Usually what happens in memory when you statically allocate memory, like declare variables at the beginning of the function, they're put on the stack and it grows downwards from the top of memory, meaning it starts low in memory and starts incrementing up. And then if you dynamically allocate memory, it goes into a place called the heap, which is the opposite end. And normally the stack and the heap grow toward each other. We don't ever have to worry about that. All right. That shit was a mess, said Nuri. Oh, you connected between vacuum tubes. Yeah, you have to remember, back in the day, people really did program straight in binary and do all this shit on their own. And we are maybe going to be doing that. You sure are not Bob Ross. Damn right I'm not. So anyway, where were we? We were here, and we were comparing in. I don't even know what the hell instruction that is, so let's look that up. 686 in. Whoa, what? Hey, what? Am I still streaming? Looks like I am. What happened to my browser and shit? Oh, I crashed my browser. Sorry about that. Oh, shit, hold on. $150 people are here? Whoa, whoa, whoa. Huh? Alright, sorry folks. Something weird is going on with Chrome. What the fuck is going on here? This is totally weird. I apologize for that. Chrome must be really fucked up right now. I can't even see chat right now. Hold on one sec. Holy shit. Okay. Wow, that was fucked up. Let me get chat back. Sorry. Gained 3 more people while that happened. Ooh. Either a soundtrack. I'm not even gonna ask while you have. Alright. because I transcode Bloodborne. You fucks, I have a Let's Play going, that's why. Anyway, sorry about that. Where were we? Wow. My window is really... My window is really fucked up right now. Alright, where were we? Okay. Yeah, maybe I'll do that. Hold on a second. Alright, we're back. Sorry about that. I think we're back anyway. Yeah, I was curious what this in instruction was. What are in and out instructions? Read from a port. Excuse me. Weird. Alright. I'm guessing in is not going to do anything for me. So let's advance to... Alright, now it's going to check... It's going to OR AL, which is 41, with 0 for F9 memory. Whoa, I don't know what we're doing. Is it waiting for input here? Alright, we're somewhere we don't really want to be. So let's go back to where we were. I'm just advancing here because I don't really care. I'm waiting for a comparison to BA. Jump not 0. I'm not even sure what we're doing. I'm not sure what this is doing at all. Holy sh! We are deep the fuck in it, though. You know what, wait, let's run it again. Alright. Alright, let's run it. So it's reread memory from that same location. I don't think I've stepped into disk reading stuff. I think maybe that first breakpoint was kind of a false alarm. It was doing something else in memory. Alright, first thing it's doing is it's moving AX, the entire AX register. No, it's moving whatever is at SI, which is 90D4, which should be the BA. It's just moving that into AX. Uh-oh. Not now, honey. I was starting to get it. 23 BA. Interesting. Going back to our save state. 23 BA. Aha. I know it did. It did. Oh, did I lose the editor? Wait, where the hell is my, 0, 0 out there? Oh, the kid's got a cold. Aw. Alright. Alright, what was it? 4D74, I think? hell happened? Where did my memory? Oh, well, I know what it was. It was BA23. Yeah. 50, oh god, 55 occurrences of it. Oh, well, you know, this is the one. Alright. Okay. This read, BA23, right? Oh, check this out. Okay. I'll talk about this next time. Because it's another topic called endianness. But the thing is, if you notice, it's reading the bytes quote-unquote backwards. So BA is the first byte, and then 23 is the other. Look at that. And then the next instruction here is, I think, exchange AL, which is the lower order byte BA, with AH, the higher order byte. So to switch this register into BA23. It totally didn't do that. I don't understand. X86. Wow, I really thought... Yeah, exchange register, what the fuck? What happened here, then? Okay, whatever. We still have 20. We still have the BA right here, which is that control code, you know. So push DS. So we're gonna push 4470 onto the stack. We're gonna XOR AX and AX is exclusive OR. If I do exclusive OR on the same variable, I should end up with a 0, right? Really? We're just gonna get rid of the BA23 then? It's fucking weird. Alright, we're gonna move DS into AX into DS, so we're gonna overwrite the data segment with 0. Decrement the word pointer at 05A. Alright, if you say so. Pop the data segment, which is 4470. CLI. Clear immediate. Clear eye. Let's watch. Oh, that's a flag. So then we're gonna jump on 0. 0 flag is not 0, I think. To 218. I guess that's relative. So 218. So where we go next? Oh, we didn't jump. Okay. We're gonna move 20 into the lower order of AL. For some reason. We're gonna do out AL 00. Don't know. Out 5F. Don't know. Interrupt 1C. Are we drawing? What is that? Oh, this is such a bitch. So I jump 0 and see how we won't jump. We did jump, maybe. Anything happened in the game? No. Let's run the breakpoint again. See if it... No, it's done. Wow, I have no fucking idea what it did with the BA. It didn't even look like it tested on it. The game's running now. Wow. What was it, 70? Wait, stop. Don't do that. 70. 55. Sorry, I'm just gonna repair this. Back to the way it was. Holy shit. That was fucked up. Sable antelope. Oh, nothing. Alright, second time you hit the breakpoint. Alright, so here's our 23BA. Here's the memory. That's the bytes we're reading. I wonder why we read 2 at a time. Exchange AH and AL. I really think that should make BA 23. Why does that do that? Oh, maybe I know why. Hold on. Maybe I know why. Watch this. Alright. I'm going to step over the ALAH and it'll do what I think it's going to do. Of course it didn't. Pushes the data segment. And then it stores AX and AX, and we totally fucking lose the byte we just read. You fucking win, Dead of the Brain. I don't know what the fuck it's doing. Okay, Vector, why does it jump like that after it's changing? You fucking... Your guess is as good as mine. Why does it jump like that after it's changing? Did it even exchange? I mean, it must have, right? Alright, compare it. We compare it to 81. Jump here. Jump far, code segments. 37, right? Oh, wait, wrong one. We do it the second time. We move this into the stack pointer, right? We exchange A, H, and AL. This, I don't get why this jumps. The only thing I can think of is maybe it jumps because the debugger's fucked up and it doesn't actually work. Or I am more likely just totally misunderstanding the instructions. Looks like some compare operators are below the exchange. Jump to DE13. Hey, Target Buddy just subscribed. Thank you. Let's do this. Let's pretend this worked like we think it does. We, increment SI twice. We compare AX to FFFF. Jump off 0, which it shouldn't happen. Compare it to FFFE. What? Jump on 0. We compare AH to A0, and I'm guessing A0, I guess is 0. Should fail. We jump not into DE14. called EC E3. I just do not understand. Step over. Step over. F8. I don't get where the hell, why that just went there. Oh wait, look at that. 23BA is back. Push ES. Back to the code segment and just blows it away again. 0. I don't think it's reading anything into AX. I don't see the BA23 anywhere in these registers or anything. I'm just hitting F7 like over and over again. Hopefully like something gets popped. We do return. I should have been watching the stack pointer actually. Oh, wait, it's back. CLI. Push AX. Don't push AX. It's going to go away, that means. 2320, yeah. Alright. Pop AX. When I pop AX... No, wait. How did we get here? Oh, my lord. There. Alright, we're back to 28.3b. We're going to I return. Now we're going to exchange AH and AL. We jump again. What the fuck? Wait, oh, whatever. If you're lost, so am I. Alright, hold on. I'm not out yet. Let's set another breakpoint. Here. Okay. Okay, let's run it. Okay. 81E3. So it's going to compare 81 again. So it's going to compare 81 again. It's going to fail. It's going to jump. Eventually, it's going to read the shit into AX. And I totally forgot what AX should be. It's another BA23. This is a fucking nightmare. I might call it. I feel like I'm staring into the abyss here and I'm kind of losing track of what I'm even doing. Well, maybe we learned some stuff. I didn't learn what I wanted to, though, which was like all the different things. Frankly, it was way more efficient to just try shit out and see what happens. So yeah. I mean, you know what? We know 81 does something fucking weird. right? So let's toggle breakpoints. I just want to do something odd before we call it. Let's just put a fucking 81 here and see what happens. I'm curious. Oops, no. You thought it was so fucking important, dead of the brain. Show me what the hell happens when I put it there. The answer is nothing, of course. Wait. Don't pause. I'm done with this crap. There. 81. Oops. I told you to toggle the breakpoint. Whoa. No, I don't want a breakpoint there. Oh, that's how you set instruction breakpoints, I guess. '81 didn't do a fucking thing, it looks like. Totally fucking weird. I feel like there's still... This is 2D. Alright. Let's try something else, too. Let me get rid of this. Oh, I get it. Toggle breakpoint. That's what I meant. Take breakpoint off of here, off of here. Close our windows. All right. What do I want to do? To C, G, to E. Curious what happens here. Breaks the game. 2C is bad code. So 2F seems like the lowest hiragana we can make. Is that really true? Lowercase e, it should go earlier than that. Two C broke it for some reason, right? And yeah, 2C breaks it. And the highest order byte we ever go is 7F, so 80. Yeah, sure. What the hell? Let's try 8065. Why not? Yeah, good. Wait. Wait. Whoops, no, I didn't want to do that. Alright, yeah, I'm starting to lose focus now. Yeah, right. I don't get it. 80 is like nothing, or what? Yeah, I guess 80 is nothing. Totally weird. Alright, well, sorry folks, we didn't get as far as we wanted tonight. But, you know, I guess hopefully it was educational on some level. I don't know, I was hoping to get a little further. Honestly, this x86, I'm going to have to read more about x86 and figure this out. Alright, have a good one.